Hi everyone. I'd like to thank the organizers for the kind invitation and the opportunity to participate in this workshop. Also, my apologies to those of you who have already heard this once before. So I'd like to talk about some joint work with Ed Kroc, where we study the relation between the three objects in the title: Lacunarity, Kakeya type sets, and directional maximal operators. So a good place to start is with a classical construction of Besikovich, in 1928. So what I'm about to say is not exactly what he proved, but certainly this is one of the most popular renditions of it. In R2, given any epsilon positive, there exists an integer n and rectangles Rj so there are exactly 2 to the n of these rectangles, and these have dimension 1 by 2 to the minus n, with 2 to the minus n separated directions. With the following properties: that they have considerable overlap so much, in fact, that their union in volume is smaller than the epsilon that you chose, and yet when you translate each one of these rectangles, and I'll explain by how much, they all spring apart and become disjoint. So what's Rj tilde? Rj tilde is what is typically referred to as the reach of the rectangle. So if this is Rj, this is 1 and this is 2 to the minus n, then Rj tilde is when you translate Rj along its axis by twice that amount. So this is Rj tilde, leaving the dimension unchanged, of course. Okay. So there are many implications of this result, but probably the most immediate and also chronologically the most important is that it establishes the existence of sets in R2 of arbitrarily small measure containing a unit line segment in every direction. And of course, these are what are called Kakeya type sets, Kakeya sets. But that's one corollary of it, but that's by no means all. A number of remarkable results in harmonic analysis and elsewhere have relied on the existence of such rectangles. So just to cite some examples, if you think of the proof that differentiation fails for averages of rectangles of arbitrary dimension and orientation in RD, that relies on this fact. And another example is Pfefferman's celebrated counterexample of the ball multiplier. Okay, so this construction continues to be the main motivation for the definition that I'm about to write down. So let omega be a set of directions in RD plus 1. Let's say, so we are going to say that omega admits Kakeya type sets if for all integers n, there exists a small constant delta n and tubes are obvious are cylinders with circular cross section and long length, and tubes PT with length larger than 1 or equal to 1, and cross-sectional radius delta n, for which something similar to this is satisfied, namely these tubes and their extended versions have widely disparate volumes. So for which En and En star obey the relation that the ratio of their volumes goes off to infinity. So what is PT star? Well, so if this is PT, PT star is another tube with the same center, orientation, and cross-sectional radius as PT, but a constant times its length. So if this is L, this is some C0 times L. So the question that I'm going to be interested in this talk is the following. Which direction sets omega admit Kakeya type sets? Okay, so to understand why such a question is of relevance, so let me introduce, at least as part of that, two maximal operators. Widely studied in harmonic analysis. The first one, d omega, is the directional maximal operator associated to the direction set omega. So what does it do? So it takes the soup of the averages of absolute value of f over all line segments centered at the point x, but whose orientations come from omega. And a related object is a Kakeya Nicodem type maximal operator, m omega. Once again, something similar. This time, you take the soup of the averages of absolute value of f over all possible tubes. This time, the tubes have to be parallel to omega, but can have arbitrary dimension otherwise, and they have to contain the point x. Okay. So one fact that I'm going to refer to a few times in this talk is, I'm going to call it fact star, is that if a direction set omega admits Kakeya type sets, then both of these maximal operators are unbounded on all the non-trivial Lebesgue spaces. So if omega admits Kakeya type sets, are unbounded So how do we know this? So this is a very standard argument. So I can just quickly run through this with you. So if you choose a point x that belongs to one of the extended tubes, En star, so that means that there must exist some tube so that x belongs to Pt star. And that implies that if you now evaluate the directional maximal operator on the test function, which is the indicator function of En, that is definitely bigger than or equal to the integral and L here is the length of Pt. So what that means is if you just evaluate what this is exactly a constant. So this contains a Pt which has length L, therefore this is bounded from below by a positive constant which doesn't depend on anything else. Okay, so what that implies is that the LP norm, so using these as the test functions, you obtain a lower bound on the LP operator norm of d omega, which is this ratio, and of course the definition dictates that this goes off to infinity. Okay. So the admittance of Kakeya type sets implies unboundedness of certain operators, but of course in order to understand this question really well, we have to make sure, among other things, that this is not a vacuous conditions, and there are actually examples of omega where these operators are genuinely non-trivial and bounded. Okay. So here are some examples. So on the other hand, here we go. So So what I'm about to set down is a list of examples in all of which both of those operators will be LP bounded, not just for some P, but in fact for all P, except possibly one. All right. But d omega and m omega are both LP bounded. For p strictly between 1 and infinity in all of the following cases. So the first work in this direction was pioneered by Nagelstein and Wenger. In 1978. And the example that they considered is the following. So it looks like this. So I'd better explain what's what. So A1 through AD plus 1 are positive distinct constants. Okay. And the theta j's, it's a Lacunary sequence. In other words, that goes to 0. So theta j plus 1 is less than or equal to lambda times theta j for all j bigger than or equal to 1, and some lambda strictly smaller than 1. Okay. All right. Shortly thereafter, in 1981, this was extended by Sjogren and Schollin in the planar setting. And so they called it a planar Lacunary set of finite order. I'm not going to get into their definition, but I'm just going to give you an example which tells you what kind of sets fall under their paradigm. So for example, if you build up your sets using geometric sequences, for example, say sets of this form. So I should say sets of this type. Okay. Now, this result was subsequently extended and placed in a slightly more general context later by Alfonseca, which in turn builds upon joint work of Alfonseca with Soria and Vargas. In 2003. In 1988, another example was studied by Carberry. So the example that he considered was the Cartesian product of a geometric sequence. So omega c look like this. Okay. And finally, in very recently, in 2013, a definition of lacunarity of finite order was proposed by Parset and Rogers. Where once again they show that, which in particular subsumes all of these previous cases, and they show that under their definition, these operators continue to be LP bounded for all these range of P. Okay, so there do exist honest examples of bounded directional maximal operators. However, to balance this out, I might as well show you two counterexamples. So one of them is the following. It's the direction set is planar. So omega is of the form cosine theta sine theta, where theta belongs to the Cantor middle third set. This example was studied by Bateman and Katz. In 2008. And the methodology introduced in this paper was very important to our work. The second one is due to Parset and Rogers and appears in the same paper that I mentioned above. And that example is the following. So in a sense, it's sort of similar to the Nagelstein-Wenger example. What are the QLs? Well, the QLs is the enumeration of the rationals in some non-trivial interval. Let's say just say centered about 1. So what Bateman and Katz showed is that omega, as in here, admits Kakeya type sets. And maybe if there is some intuition to be gained from the list of examples that you see on this side, that's not so surprising, because all the examples over here have this feature that they use lacunary sequences or geometric sequences as building blocks. Certainly this doesn't fit that profile. On the other hand, this is somewhat surprising, because here you have a direction set. Each coordinate projection is a geometric sequence, and yet what Parset and Rogers show is that D is unbounded for all P. Okay. All right. So nonetheless, the intuition that is gained from studying these examples turns out to be the right one, at least in the planar setting. So I would like to give you first the planar characterization for existence of Kakeya type sets and directional maximal operators. But before I do so, I should make it clearer what lacunarity in dimension 1 means. Okay, so what is lacunarity on R? All right, so let's start with the definition of a lacunary sequence. So a sequence A lambda consisting of the points AJ is lacunary with lacunarity constant at most lambda if there exists a number alpha in R, lambda less than 1, such that for all j, the distance from aj plus 1 to alpha is no more than lambda times the distance of aj from alpha. All right. So we use these lacunary sequences as the basis for defining a general lacunary set on R. So we are going to say that a subset U of R is lacunary of order 0 if it's either empty or a singleton. That's not very edifying, but we say that it's lacunary of order n with lacunarity constant lambda. So if there exists a lacunary sequence, so for now, just to keep things simple, I'm going to assume that U is relatively compact. So if there exists a lacunary sequence A lambda with the following properties, that U is completely contained between the inf and the sup of this sequence. And most importantly, for any two consecutive elements AB in lambda, the restriction of the set U with the interval AB is lacunary of lesser order. Okay? In other words, what I'm trying to say is that you declare a set to be lacunary of order n if you can find a demarcating lacunary sequence with this property that when you look at these chopped up pieces, these blocks from this demarcating sequence, they have to be of smaller order. Okay? All right. So with this definition, it is not at all hard to see that if you look at 2 to the minus j, the lacunary sequence, that's lacunary of order 1. If you look at that set 2 to the minus j plus 3 to the minus k, that's lacunary of order 2, and so on. Okay? And we are going to say that U is sublacunary if there does not exist any integers n and r or lambda smaller than 1 such that U is coverable by R members. So R sets that are lacunary of order n. So the reason for writing this definition down is to point out that this is exactly what is needed to tie into the other two concepts of admittance of Kakeya type sets and directional maximal operators that I mentioned before. So the result that I would like to, so I want to mention is the following. So here's the theorem. This is in dimension 2. So d is equal to 1. It says that you have a direction set omega, which is cosine theta, sine theta. And theta is the set of angles for your direction set. Then the following statements are, the three following statements are equivalent. Number one is that omega is sublacunary. Two, that omega admits Kakeya type sets. And three, d omega and m omega are unbounded for p between 1 and infinity. Okay, so the implication 1 implies 2 is due to Bateman from 2009. The implication 2 to 3 is just fact star, which I have already given you a proof of. 3 implies 1 is contained in the work of Alfonseca, also mentioned earlier. So some of these implications actually admit stronger versions. So the whole story is not quite here. What Alfonseca ends up showing is that if omega is lacunary of finite order, then not only are these directional maximal operators bounded for some p, which would be the right conclusion, it's in fact bounded for all p in this range. So there's an interesting dichotomy here. Either these operators are unbounded everywhere for all the big spaces, or are bounded for all of them. Okay. So a question of interest is to identify conditions under which or appropriate analogs for which one could obtain similar characterizations in general dimensions. So that's what I would like to talk about next. Okay, so before I launch into a definition, it's worthwhile identifying at least some of the challenges that lie in extending the definition of lacunarity to higher dimensions. So one, fact to be aware of is that lacunarity is not preserved under set algebraic operations. So what do I mean by that? So what I mean is, if you take two sets, A and B, both of which are lacunary of finite order, and if you look at A plus B, then there is no reason to believe that it's going to be lacunary of finite order, even though that initially may seem counterintuitive. So here's an example. So suppose you take U to be, so once you know what to look for, these examples are by no means rare. So suppose U is a countable union of Uj, and each Uj looks like this. And capital Nj is a fast growing sequence relative to Mj. So just to draw a picture, so here's the origin. And you have these dyadic intervals. And so on. And in each of these, you are putting a point. This distance being qj1, this being qj2, and so on. Okay. So what are the qjk's? Well, you have a lot of choice here, but the point is to sort of choose it so that they are equispaced. So just to give an example, you could choose qjk to be so it has to be an affine copy. So this kind of dyadic rationals will do. Okay, so that's U. Certainly, as you can see, every interval of the form 2 to the minus L to the minus L plus 1 will contain either exactly 1 point or nothing, depending on how fast the NJs grow. And your V is much, much simpler. It's simply the negative 2 to the minus J. So what we see immediately is that both U and V are lacunary of order 1. And yet, when you look at U plus V, that will surely contain, after cancellation, these qjk's. In other words, they will contain affine copies of more and more equispaced points. Such a set, U plus V, cannot be lacunary. U plus V is sublacunary. Okay. So this is still a statement about one-dimensional sets, but it does illustrate one obstacle towards readily extending the notion of lacunarity in one dimension to 2 dimensions. So, for example, what would you say should be the destiny of U cross V? That's a set whose one-dimensional coordinate projections are lacunary as well, very nice, and yet when you take that set and you rotate it by 45 degrees, suddenly it so happens that that set has lost all its beautiful lacunarity properties and one of the projections has become sublacunary. So that's sort of something to be aware of. Okay, so here's the definition then. So suppose you take U to be a subset of Rd. You say that U is lacunary of order n, and write that U belongs to lambda d. Or maybe let me say the following. U is a lacunary of finite order. If there exist n and r bigger than or equal to 1 and lambda less than 1, such that for all lines L in Rd, the projection of U on the line is coverable, can be covered by R sets in lambda 1 and lambda. In other words, sets that I have described already up there. Okay? And if that happens, then we are going to write U to be this and declare n to be the maximal lacunarity order of U. Okay, so we require this from all lines uniformly in the lines. Some examples, quick examples are in order. the sets considered by Nagelstein-Wenger and Carberry are both lacunary of order 1 and d plus 1 respectively. So loosely speaking, these numbers reflect the number of free parameters used to describe those sets. And on the other side, if you wanted some examples that are not lacunary of finite order, so for example, a curve in space would do it, but that's probably overkill. In fact, any subset of a curve which has positive Hausdorff dimension would do it. Okay, so a curve in R3, or for example, U cross V as above are sublacunary. Okay, so we have now a notion of Euclidean lacunarity. We still need to tweak this a bit to understand what we mean by lacunarity of direction sets. So we have lacunarity of direction sets. So we are going to say that omega subset of R d plus 1 is lacunary of finite order as a direction set if you look at the cone generated by this direction and intersect with any hyperplane, this belongs to so if you require that there be an n and an r and a lambda less than 1, such that this has to be true for all hyperplanes V not passing through the origin. Okay. And if that doesn't happen, call it sublacunary. All right, in other words, and what is C omega here? C omega, as I said, is the cone generated by the directions, the vectors in omega. Okay, so in other words, you require the existence of these parameters which works uniformly for the intersections with all planes. And it's not surprising that the Nagelstein-Wenger and Carberry examples continue to fit this profile with the same values of n as above. And another example to contrast that with is the one by Parset and Rogers that I mentioned earlier. Okay. And this is where you see, so if you look at what the cone generated by this direction set is with this hyperplane x2 equals 1, that's the bad hyperplane here. And what you end up getting is this collection. And of course, now it's very clear that when you project onto the x1 axis of this projection, this is what makes it sublacunary. Okay. So the result that I wanted to talk about is the following, that if omega is sublacunary in the sense just described, then omega admits Kakeya type sets. Okay. So if you combine this with the other results that I have already talked about, what one obtains is a characterization exactly in the same flavor as the planar one that I mentioned already. So for example, in dimension D, in general dimensions, the following statements are equivalent. Omega is sublacunary. Omega admits Kakeya type sets. And d omega and m omega are unbounded on LP for all p between 1 and infinity.
So Malabika, if you
yes.
require this to hold for fixed and an R, you want it to hold for all hyperplanes, not passing through. So you're not allowing it to be in a different type of class.
Meaning, are these numbers allowed to depend?
You're fixed, yeah, it's N and R first.
Mm-hmm.
You're requiring it to
yes.
the same class for all hyperplanes.
That's right. But of course, you realize that these classes are, as n increases and r increases, there is a containment within this class. So it's just that everything has to be capped out by a finite number. I'm not saying that for a given hyperplane, this is like the optimal n. It's just that it cannot exceed that n.
It's not enough to check that condition on finite.
Well, I think it is. It's something that we are actually working on to understand exactly how, if we start with a set that is Euclidean lacunary, what else can we check this on finitely many hyperplanes and still be able to do it? And I think the answer is yes, but let me not mouth anything off right now. Okay. All right. So where am I? Okay. So this, if omega, so this for d equal to 2 was due to Bateman, as I mentioned. And for d bigger than or equal to 3, this is our claimed result. 2 implies 3 is fact star from the very beginning, which works in all dimensions. 3 implies 1 is Alfonseca in dimension 2. And essentially based on localization principle due to Parset and Rogers in high dimensions. Okay. All right. So in the couple more minutes that I have left, maybe 1 minute that I have left, what I will try to do is to just give a very quick overview of what's involved in the proof without getting into details of any kind. So, sketch of proof. So what exactly is it that we are up to? We would like to show, starting with a sublacunary direction set, that it admits Kakeya type sets. In other words, we are trying to find a collection of tubes pointed in the directions from omega so that somewhere they have a lot of interaction and somewhere else they have essentially no intersection at all, so that when you look at the ratio, that will show up the disparity in the volumes. That's what we really want to do. Okay, so here's the idea. So we first have to locate a hyperplane, and as we will understand this hyperplane, so the hyperplane has to be somehow connected with a bad hyperplane that comes from the definition of Lacunarity, that's x1 equals 1. So we look at the parallel hyperplane passing through the origin, and we split it into small cubes. On each such cube, these are going to form the roots of the tubes that I will construct, and each one is going to be assigned a slope. Okay? So what we end up assigning is some carefully chosen families of tubes. So what we need, we need tubes to not intersect very much, near x1 equals 0, but to intersect, to have a lot of intersection near x1 equals 1. Okay. So the way we go about doing this is, so the broad strokes of the proof follow ideas that were already present in the work of Bateman and Katz, and subsequently Bateman's proof for the planar characterization of Kakeya type sets. So the first thing is to establish a relation between Euclidean lacunarity and planar and tree lacunarity. So what do I mean by tree lacunarity? Well, all of these sets can be expressed as a tree with respect to a fixed base. And it turns out that the notion of Euclidean lacunarity can be translated to statements about how rays in that tree behave. In particular, one can say that if you have a sublacunary direction set, so for example, one can say that there exists a hyperplane V such that every ray so given any capital N bigger than or equal to 1, there exists a hyperplane V, so that every ray in the tree that depicts the cone, that's cone intersected with V, splits at least n times. So there are results in this genre. And the next thing is, once we have some knowledge about the structure of this tree, there is a pruning mechanism to kind of trim it down to the barest essentials. In particular, once you know that this tree splits at least n times, by an appropriate pruning process, you can make this tree look like an elongated binary tree. And the choice of, so I said, my goal is to assign slopes to roots so that I have tubes. This selection, the method of assigning slopes to roots is a random algorithm based on this tree. So the final is a random algorithm that assigns slopes to roots and this exploits the notion of stickiness. So what exactly is stickiness? It's a notion that has appeared many times in the past in the study of Kakeya type sets, originating possibly in the work of Tom Wolfe, but certainly explicitly stated with this nomenclature in the work of Katz-Tau and Katz-Tau in their study of Kakeya sets. Roughly speaking, what it means is that in a Kakeya type set, tubes with, you need the tubes to not intersect close by, but to intersect far away. And one way of ensuring that is to make sure that the roots that are close by receive slopes that are close by, so that thereby forcing an intersection, if there is an intersection, to be far away. So that notion of stickiness has many manifestations. In this case, it sort of comes about in this random algorithm in the way that we assign a ray in the root tree to a ray in the slope tree. Okay, so I think I should stop here. Thank you. That's right. So you have the bad hyperplane, and you have a set inside that hyperplane. Okay. Now I am going to the moment I say that I'm going to express this set as a tree, I have implicitly assumed a coordinate system. Because after all, what exactly would the tree do? The tree would pick out precisely those dyadic or imadic cubes which contain these points. That's what the tree representation does. In order to come up with such an imadic cube, there has to be a choice of a coordinate system within that hyperplane. So the choice of the axis there is determined by these bad lines. So you first find a bad hyperplane. The bad hyperplane is a bad hyperplane because there is a bad line in that hyperplane. Use that bad line as one of your coordinate axes inside it.